Hi, my name is Ali, and today I'll be going over the video problem for assignment 2. This problem deals with a coaxial cable, and we need to find the capacitance of it. So the first thing we do is we make a diagram of it. We have the inner conductor, outer conductor, and point B where the permittivities change. So we also know that the inner conductor is positive and the outer conductor is negative. So the electric field is going to be going radially outwards. Now we need to find the boundary conditions. So we take a chunk of this boundary and we see what's happening across it. So we see that the electric field is actually going from permittivity 1 to permittivity 2, and it does not have any tangential components. This can also be thought of as a series resistor. So since the electric field is not tangential to the boundary conditions, it's normal. The electric field is actually changing with the two permittivities. But this means that the electric flux density, which is permittivity multiplied by electric field, is the exact same for both the regions. Well, this is because the electric flux density over here is the exact same electric flux density here. This is because the electric flux coming out of this area is going straight into this area, or coming out of that boundary. That's how I like to think of it. So now we need to find its capacitance. So we can first find the enclosed charge, and we can do that by assigning positive Q to the inner conductor and negative Q on the outer conductor. And then we can draw it in cylindrical coordinates, because we need a Gaussian shape, and cylinder would be most fitting because our coaxial cable is a cylinder. And once we found the surface area of the cylinder, we know that we won't need to be using top and bottom because they are tangent to the electric field, so there's no flux through them. So we simply dot these two terms, and we are left with this equation in which we can sub in the entire equation for electric flux density, which is epsilon E, and we get an expression for electric field. Now that we have our electric field, we can find our voltage using the formula sheet. We can find the potential difference equation and the dl for a cylindrical in cylindrical coordinates. So now we need to solve this integral. So first we just dot these two terms because they both have a hat r. So now that we have our integral over a to c, we need to actually put this over a to b and from b to c, because there are two regions in this, and we need to account for both. It's not just a one region thing. So now we need to take out our common factors, such as these ones. We leave in epsilon 1 and r, but everything else gets taken out because it's common to both integrals. The epsilon 1s and 2s are just taken out of the integral because it's specific to that integral. Like region a to b has the permittivity of epsilon 1, and regions b to c has the permittivity of epsilon 2. So now we solve the integral. It gives us ln, and we know that ln a minus b is just ln a over b. Same case for b over c. And then we can put it over the same denominator by multiplying across, both multiplying this term by E2 and by multiplying this term by E1. And we're left with this equation. Now we can get rid of the negative by putting it into the lns, because if you put a negative into a ln, it just flips the order. Rather than a over b, it's going to be b over c. So that's what we did here. The b over c is turned to c over b. The a over b is b over a. Now, just a quick clarification, we can use this equation and it would still give us the same answer for capacitance. This is just the simplified version of it. And now we're near the end. The capacitance is just charge over voltage. We have charge, we have voltage. So now we just cancel out the Q. And this is our capacitance. The total capacitance is given by 2 pi L epsilon 1 epsilon 2 over epsilon 1 ln of C over B plus epsilon 2 ln of B over A. That is the total capacitance. Thank you for watching.